Welcome to the Explainer. Have you ever been sitting on a plane, cruising at 35,000 feet, and just thought to yourself, how? Really, how is this happening? Well, today we're pulling back the curtain and getting into the incredible physics that makes flight possible. Right? It really does seem to defy logic. You're talking about a machine that weighs as much as 100 cars, just hanging out in the sky. But it's not magic. Not by a long shot. It's an amazing dance of physics and engineering, and we're going to break down every step. So, here's our flight plan. We'll start with the 4 basic forces at play. Then we'll dive into the secret of the wing itself. After that, we'll talk about a very real danger called a stall. We'll see how planes get that extra oomph they need for takeoff. And finally, we'll push the envelope and talk about breaking the sound barrier.
All right, first things first, you have to understand that any plane in the air is in the middle of a constant, invisible tug of war. Every single second of flight is a balancing act between 4 fundamental forces of nature.
And here they are, the 4 main players. You've got thrust, which is the engines blasting forward, fighting against drag. That's just the air pushing back. Then you've got the big one, lift, the upward push from the wings, which has to fight the plane's weight, which is gravity constantly trying to pull it down. For a plane to fly straight and level, those forces have to be perfectly in balance. So that brings us to the million-dollar question. Where does that magical force of lift actually come from? Well, the secret isn't in the engines, it's in the absolutely brilliant shape of the wing. If you were to slice a wing open and look at it from the side, you'd see this shape. It's called an airfoil. And notice, it's not just a flat board. It has a special curve on top, and it's flatter on the bottom. That curve is everything. It makes the air going over the top travel a longer path, meaning it has to move faster than the air underneath. And that speed difference is the key to the whole operation. Now, not all airfoils are the same. A fighter jet built for crazy aerobatics might use a symmetric airfoil, but the plane you fly on for vacation, that uses what's called a cambered airfoil, with that signature curve on top. Why? Because that faster-moving air on top creates a low-pressure zone. Meanwhile, you've got slower air underneath creating higher pressure. And what does high pressure do? It pushes up. That pressure difference, pushing up on the wing, that's lift. It's that simple and that brilliant. Okay, so if the exact curve of the wing is so important, you know engineers aren't just sketching these things on a napkin, right? They need a rock-solid, precise way to define and share these designs. So how on earth do they do that? They use a system, and one of the most famous is the NACA code. Let's crack it together. You might see an airfoil called a NACA 2412. That's not just a random number, it's a recipe. The first number, the 2, tells you the max curve, or camber, is 2% of the wing's front-to-back length. The 4 tells you that the highest point of that curve is 40% of the way back. And the last 2 digits, 12, mean the wing's thickest point is 12% of its length. It's like a secret code for creating the perfect wing. But here's the thing. A wing can only generate so much lift. You can't just keep asking for more and more and more. If you push it too far, you can get into a really dangerous situation where the lift just disappears. It's called a stall. To get what a stall is, you need to know about the angle of attack, or AOA. It's just the angle between the wing and the air rushing towards it. A pilot can increase lift by pitching the nose up, which increases that angle. It works, but only up to a certain point. So picture this. The pilot pulls back on the stick, the nose goes up, and the lift gets stronger. Great. But if they keep pulling back, they hit the critical angle of attack. That's usually somewhere around 16 to 20 degrees. Tip the nose just a tiny bit past that point, and the air can't follow the curve of the wing anymore. It separates, becomes turbulent, chaos, and poof, the lift is gone. And this is so important to understand. A stall has absolutely nothing to do with the engines. The engines could be running at full power. A stall is purely about the wings losing their grip on the air. It's an aerodynamic problem, and it's why pilots train endlessly on how to avoid it and recover from it. This all leads to another question. If you need speed to generate lift, how does a gigantic airliner get off the ground when it's moving pretty slow on a runway? How does it land slowly without stalling? Well, it gets a little help from some clever engineering. That help comes from what we call lift augmentation devices. And if you've ever sat in a window seat over the wing, you know exactly what I'm talking about. It's those loud whirring and grinding noises you hear before takeoff, as you see parts of the wing literally extend and change shape. They are temporarily reshaping the wing to make more lift at low speeds. Our high-lift heroes are two main devices, slats and flaps. Slats are on the front, or leading edge of the wing. They pop out to let the wing fly at a higher angle without stalling. And flaps extend from the back or trailing edge. They basically make the wing bigger and more curved, which squeezes out every last ounce of lift possible. And the difference they make is just incredible. Look at this. A clean wing, all tucked in for cruising, has a certain amount of lifting power. But deploy the flaps and slots for takeoff, that power jumps way up. And for landing, with everything hanging out, they can literally double the wing's lifting power. That's what allows a massive jet to approach the runway at a safe, manageable speed. Okay, so we know how to get in the air and how to land safely. Now let's talk about going fast. And I mean really fast. The kind of speed where the air itself starts to behave differently, and you run up against the sound barrier. When you get into these high-speed regimes, you stop talking about miles per hour. Instead, everyone uses the Mach number. It's super simple. It's just your speed compared to the speed of sound. So Mach 1 is the speed of sound. Mach 2 is twice the speed of sound, and so on. It's the universal language for flying fast. So you can see flight is broken down into these different zones. Almost all of us fly in the subsonic realm, below about 80% of the speed of sound. Then there's the tricky transonic zone, where some parts of the plane are breaking the sound barrier while others aren't. Go faster, and you're supersonic, the world of fighter jets and the legendary Concorde. And the next frontier, that's hypersonic, flying at more than 5 times the speed of sound. So you see, flight is this amazing dance. It's a dance between 4 forces, between speed and shape, between human ingenuity and the laws of physics. We've managed to harness these invisible forces to do something that once seemed impossible, which really makes you wonder, what other invisible forces are out there, just waiting for us to figure them out?